All right, physics. We're going to talk about Newton's second law today. And again, I would have a piece of paper that you can take some notes on. And we're going to talk about Newton's second law of motion today. So hopefully you remember Newton's first law because we just talked about it. Newton's first law is an object stays at rest unless acted on by an unbalanced force, or an object stays in motion unless acted on by an unbalanced force, right? So it stays at rest or it stays in motion. In other words, there's no acceleration whatsoever, right? Well, what happens when there is a force that's unbalanced? When there's two forces opposing, but one's bigger than the other, we would say overall there's a net force. What happens? Well, acceleration happens. We get an object to accelerate in the direction of the net force. So here's what Newton's law says. Newton's law says, an unbalanced force on an object causes acceleration in the direction of the net force. And usually when we talk about Newton's second law, you see this equation. Net force, that is the sum of the forces. That's what that means right there. The sum of the forces is equal to mass times acceleration. Now, with Newton's first law, you actually saw that idea before. We said net force, like in the y direction. Remember, we had like Fn plus Fg, and we added those together. We set them equal to 0 because there was no acceleration in the x direction. The only difference here with Newton's second law is when we have a net force and it's not equal to 0, we set it equal to mass times acceleration for that object, okay? All right, so that is our equation, and we're gonna do a couple of sample problems here, so please kind of work through these as we go. The first question here says we have a 1,500 kilogram car is accelerating on the highway with a net force of 5,000 newtons. Draw a free body diagram. The first thing we're going to do is we draw a free body diagram, and then we're going to write summation statements. Okay, so this car, right, it's zooming down the road. I can't really draw, so hey, that looks like my minivan that I draw. It's zooming down the road. Okay. And it's accelerating. So here's what we're going to do. We're going to draw the forces. There's my car. Okay. We have the force of gravity acting on the car. That's the weight. Straight down. And then we have a normal force that must be equal in the up direction. No, we know that those are equal to each other because the car's not accelerating up or down, right? And then to the right, again, we're kind of assuming in physics, we always move to the right unless told differently. We're going to cruise down the highway with an applied force, right? And it says it's accelerating, okay? So what does that mean? And that means that there must be a bigger force to the right than there is to the left. Now, one thing you want to account for is there still is going to be friction. Sometimes it's kind of an understood thing in the problem. You kind of need to know that unless I tell you differently with objects, you're going to have some friction if an object's moving across the surface. So we are going to put a force of friction back in the other direction, opposing the motion, but that force of friction must be smaller than the applied force. Otherwise, it wouldn't be accelerating, right? Okay, and then our summation statement. So the net force in the y direction, or the sum of the forces in the y direction, is normal force plus the force of gravity. They would add up to be 0. And one of the main reasons we do that is so that you really see that those two are equal to each other, so that if we have to at any point find a normal force or force of gravity, we know that those two are actually equal. In the y direction, x direction, we do have this applied force to the right plus the force of friction to the left, but those are not equal to 0 when we add them together. They're actually equal to ma because we have acceleration occurring with this car, right? All right, next thing we're going to do, that was part A. Part B says find the weight of the car. The weight is the force of gravity, which is just mg. So we're going to say that mass is 1,500 kilograms. We're going to multiply it by 9.80. Remember, we tend to drop the negative here because we know the force of gravity is downward. So we're going to take 1,500 times 9.80, and you get 14,700 newtons. That is the weight of the car. Next thing we're going to do, it says find the acceleration of the car. Well, we have a net force equation here that has acceleration in it. And if you look back at the top, it does tell us that our net force is equal to 5,000 newtons. So net force is equal to MA. We know that if we added the applied force, which we don't even know what the applied force is, or the force of friction, but if you were to add them together, you would get a positive 5,000 newtons. And we're going to set that equal to mass, which is 1,500 times the acceleration. So all we're going to do is divide our 5,000 net force divided by 1,500, and we get an acceleration to be 3.33 meters per second squared. There's our acceleration. Okay, now, next question says, if the car started from rest, how fast will the car be moving after 10 seconds? We are not going to get away from kinematics, so you're going to have to be okay with it. This car starts from rest, that's V0. How fast will it be moving? Hey, we're finding V final, and we know that the time is 10 seconds. And hey, we just calculated acceleration. So we need an equation. Don't worry, I'll give these to you, or you'll have access to them. We need an equation that looks like this. V final is equal to acceleration times time plus our initial velocity, where our initial velocity is 0, so I'm not even going to use that. I'm going to cancel that out of my equation. V final here is going to be acceleration, which is 3.33, times my 10 seconds. So V final is going to be 33.3 meters per second. If you need a reference for that, that's about 75 miles per hour. There you go. First problem done. Let's move on to the second one. Second one is all about a hockey puck. Hockey puck is traveling at 20 meters per second, and it slides to a stop in 4 seconds. So we've got this surface of ice. Hockey puck, it's moving this way, but as it moves to the right, it's actually slowing down. Something is causing it to slow down. There must be some friction between the hockey puck and the ice. Okay, first thing we're going to do, free body diagram. We've got the hockey puck, force of gravity, straight down. Normal force, the ice pushing up on it, must be equal to the force of gravity. So there's a normal force upward. What other forces are acting on the hockey puck? Well, is there a force to the right? It's moving to the right, but there isn't anything in contact with it. And so therefore, there actually is not a force any longer pushing it to the right. At some point, maybe a hockey stick hit it or somebody kicked it. Somehow it was moving to the right, but there's no contact still. So the only force acting on it is what's slowing it down, and that would be friction. Friction always opposes motion. So if the hockey puck is sliding to the right, friction must be in the other direction. That's it. That's the only three forces acting on our hockey puck. We're also going to do summation statements. So in the y direction, normal force plus force of gravity is equal to 0. Hey, that's Newton's first law, right? No net force. There's no acceleration. In the x direction, though, we only have one force of friction. And we set that equal to mass times acceleration, right? All right. So now it says find the acceleration of the puck. Looking at that equation we just wrote, here's the problem. We don't know the force of friction, and we don't know the mass. So we actually have to go back to kinematics, and we think about the things that we know. We know that the initial velocity of the hockey puck is 20 meters per second. We know that it's going to come to rest. That would be 0 meters per second. We know the time it takes is 4 seconds. What we don't know is acceleration. Hey, here's the equation again. We're going to use this VF is equal to AT plus V sub 0, and we're going to solve for acceleration. Our final velocity we said was 0. Our acceleration we don't know. The time is 4 seconds, and our initial velocity is 20. So we have to get A by itself. First thing I'm going to do is I'm going to move my initial velocity over, move it to the left side. So we're going to subtract 20 from both sides. And then we're going to set that equal to A times 4.0, right? So I moved this over. The next thing I'm going to do is divide both sides by 4, and that's going to give me my acceleration. So acceleration ends up being negative 20 divided by 4 is negative 5.0 meters per second squared. That's my acceleration I'm working with. So the acceleration is negative because it's slowing down as it's moving to the right. So the acceleration is in the opposite direction of the motion, right? Letter C, if the net force acting, it should say on, from friction, if the net force acting is from friction, I don't even know what I'm trying to say there. The frictional force is 1.9 newtons. What's the mass of the puck? So go back to our net force equation here in the x direction. We said force of friction is equal to mass times acceleration. Now remember, the force of friction is in the negative direction. So we actually have to put a negative 1.9 instead of just using 1.9. Our mass, we don't know, but we do know the acceleration is negative 5.0 meters per second squared, right? So when I divide both sides by negative 5.0, then I end up with, so negative 1.9 divided by negative 5, you end up with a mass of 0.38 kilograms. There is the mass of the puck, 3.38 kilograms. That's the same thing as saying, what, 38 grams? Because there's 1,000 grams in a kilogram, right? Whoops, 0.38. I misspoke, that'd be 380 grams, okay? All right, so we're back to, we have a mass of 0.38 kilograms. We want to know what is the normal force acting on the puck. Well, here's the good news. If we go back to our net force equation in the y direction, we already said that the normal force plus the force of gravity is equal to 0. So therefore, the normal force must be equal to the force of gravity. So all we have to do is plug in m times g, and that's going to give us our normal force, right? So we take our 0.38, we multiply it by 9.80, and that's going to give us our normal force of 3.7 newtons. There's our normal force acting on the puck, which would be an upward force. All right, that is the end of the second problem. Third problem is a little bit more complicated. It says a boy lifts a bucket of water out of a creek with an upward force of 80 newtons. If the water and the bucket have a mass of 7.5 kilograms total, what is the acceleration of the bucket? If you read further down, he's kind of standing on a bridge. So I'm going to kind of draw picture-wise what's going on here. There's a boy standing on a bridge, and he's got this string hanging down and a bucket, and he's lifting it out of a creek, right? So if I want to know the acceleration of the bucket, well, I'm going to have to think in terms of the bucket itself, and I would start with a free body diagram. It doesn't directly tell you to do this, but I would always start with a free body diagram. Think about what's going on with the bucket. There is a force of gravity pulling downward the weight of the bucket, right? And then there is an upward force. Now, if you look closely, the upward force is given to us of 80 newtons. You have to look closely here and realize if it's asking us for the acceleration of the bucket, we're assuming the bucket is accelerating upward, right? So this force upward has got to be bigger than the force of gravity downward if we're going to accelerate the bucket upward, right? Now, what type of force is it? Well, you could probably call it an applied force, but what might be better is to call it a force of tension because we are dealing with a rope or a cable pulling upward on the bucket. You could call it either one. I'm going to call it a force of tension. Is there any forces in the x direction? Nope, there's nothing pulling on it to the left or to the right. Okay, then I'm going to do a summation statement in the y direction. I've got a force of tension plus a force of gravity. Together, added together, they're going to cause acceleration. So we're going to set it equal to ma, not 0, right? Now, if you look closely here, we do know the force of tension is 80. we could calculate the force of gravity. In fact, that's what we're going to do over to the side here. We're going to take 7.50 times 9.80. We're going to multiply those together so we can get the weight of the bucket so that we can plug that into the equation. So we're going to take 7.50 times 9.8. Now, careful. The answer given to me in a calculator is 73.5, right? But here's the issue. That's not a positive number. The force of gravity is downward. So you have to consider that when we actually plug it into this equation. We're going to subtract 73.5 because it's a downward force, and therefore you don't want to have two in the same direction added together. You have to oppose because we're finding the difference between these two numbers. And then we're going to set it equal to the mass, which is 7.50 times acceleration. So if I take 80 minus 73.5, I'm going to get 6.5 newtons. I'm going to divide it by this 7.50, and that's going to give me my acceleration divided by 7.50. And you're going to get an acceleration of 0.86. Oh, let's keep it with two sig figs here, 0.86 or 8. I actually probably should use 87. I'm going to round this up, 0.87 meters per second squared. There's the acceleration of the bucket upward. Okay. Now, if the bridge is 20 meters above the water, so we're thinking here this delta y, this height is 20 meters high. We want to know how long t it's going to take to lift the bucket, right? Question is does it take very long? Well, we're going to have to go back and use some kinematics here. Here's what we know. We know delta y, we're going to pull it at distance or displacement of 20 meters. We know that the initial velocity, we're supposed to assume that in the y direction is 0 meters per second. The acceleration is 0.87 meters per second squared, and we're trying to find time. Now, what variable doesn't show up here? VF. VF does not show up. So here's what we need. We need the equation that did not have VF in it, and here it is. Delta y is equal to V sub 0 t plus 1/2 AT squared. Since the initial velocity is 0, I'm going to cross out that term. Okay, now we did this a couple different times. We did this with projectiles, free fall problems, etc. We're going to have to rearrange and solve for t. So here's what we're going to do. I'm going to get rid of my fraction first. So I'm going to multiply both sides by 2, or you can think of it as divide by both sides by 1/2. So this gives me 2 times delta y is equal to AT squared, right? We want to get t by itself. So what are we going to do? We're going to divide both sides by a. So now we have a t squared is equal to 2 delta y over a. The next thing we're going to do is we're going to do square root of both sides so that t is now equal to the square root of 2 delta y over a, right? So we're going to plug in numbers. 2 times 20 meters divided by 0.86. That whole thing gets square rooted. So I'm going to use my calculator. I'm going to go with 2 times 20 divided by 0.87, not 0.86. And then I'm going to hit to the 0.5 power. And this is going to take 6.8 seconds to lift that bucket up from the water. There you go. We're tying kinematics in a little bit back in with these net force equations, Newton's second law.